So this short video is going to be just a brief reminder of redox reactions. So in redox reactions, what we're really doing is we're talking about the electrons being transferred. So we're measuring the affinity for electrons. So I'm going to come back to this image in just a minute, and I'm going to spend some time on this table here. So what I'm talking about here is I'm talking about the measure of affinity for electrons. The example that I'm going to use most consistently throughout this demo is NAD. So one reactant is going to give up electrons, another accepts them, therefore one must have greater affinity for those electrons. And so that's what we're measuring here in our redox reactions. So the reduction potential, that's this E naught prime here, or the redox potential, is a measure of a molecule's tendency to either donate or accept electrons. And so a strong oxidizing agent readily accepts electrons, and it's going to have a positive. So if we think about the electron transport chain, the very last thing in it that accepts the electrons is oxygen. There it is. And look, it has a very positive electron potential here, reduction potential. A strong reducing agent readily donates electrons and has a negative E naught prime. And so if we look here at our NAD example, NADH, we know readily gives up its electrons, and when it does, it's going to have this negative value. And so really in this, we're also going to talk about standard reduction potential, which is the E naught prime, that's this list of values here, and our actual reduction potential. Our standard reduction potential is at a pH of 7 and 25 degrees Celsius. So this is the same as when we were talking about delta G and delta G naught prime. So one's at standard condition and one's at actual condition. The actual reduction potential is just known as E, and it's not at standard conditions. And so how are we going to be able to kind of correlate the two of them? Well, we use something called the Nernst equation. So I've written it out here. So this is the actual reduction potential. And then what we're going to be able to do is we're going to be able to calculate the actual reduction potential based on the standard reduction potential. So the E naught prime plus our RT divided by NF. So again, we have a couple known components here as we go through it. You guys are familiar with these. The only one you might not know is N. N is the number of electrons that's actually being transferred. F is Faraday's constant, T is temperature. And then we have our natural log of the oxidized over the reduced. And really what we're talking about here is the concentration of our electron acceptor over the concentration of our electron donor. So that's known as the Nernst equation. And again, that's how we're going to be able to compare our standard reduction potential to our actual reduction potential. So now what I'm going to do is I'm going to recall from freshman chemistry. So what this is this is a redox. We have our two separate chambers here, right? And what we're going to be able to do is we're going to be able to measure that reduction potential through the use of a voltmeter. So it's going to look at these in two separate containers, and it's going to look at how we transfer electrons between the two of them. And what's going to happen is that electrons are going to spontaneously flow from molecules with lower electron redox potential to molecules with higher electron potential. So that's what the voltmeter is going to read. So we're going to go back to this. So let's look at our example with what I just said about spontaneous flow of electrons. So again, spontaneous flow is that the lower the E naught prime, so our NADH is at negative 0.32, that the electrons are then going to flow to molecules with higher. So anything else higher than our negative 3.2, so anything else on this chart is going to accept those electrons. So those are where the electrons are going to flow. So what we're going to do is we have to compare electron redox potential values of half reactions. And what I want to remind you is that these particular reactions are always written with the oxidant or the oxidized molecule always on the reactant side. So we have oxidized and then we have the reductant. So please look on your handout in front of you. And what you see is we have two half reactions written. So we have this one here down at the bottom, 1/2 of oxygen plus 2 hydrogens and the transfer of 2 electrons, again that's our N value here, is going to form our H2O. And the electrons, this has a redox potential of positive 0.82. The other half reaction that we're looking at is our NAD+. It is going to have the flow of electrons plus hydrogen plus 2 of the electrons, right? So we have our 2 electrons here that are going to be transferred is going to get us NADH. And the electron reduction potential for that is negative 0.32. So whenever we're looking at these are published reduction potentials, right? So yay, we don't have to do any work on these are published. What we see is that if we're combining those two reactions together, like what's shown on your worksheet here, is what is going to flow to what. So what I want you to do is I actually want you to draw an arrow. So which one has the greater reduction potential? Well, it's obviously the oxygen, right? It has the more positive value. And so the electrons are going to flow from the bottom reaction to the top reaction. So what we're going to have to do is we're going to have to rewrite the reaction in order to make have that make sense. So what we're doing essentially is we're going to, again, electrons are going to flow to the higher electron potential, so we need to write the overall reaction. So what we're going to do is we're going to reverse the half reaction with the lower electron potential. And I've already done that for you. So if you look there, we have 1/2 oxygen, so that's going to stay the same, plus NADH, do you see how I reverse that? Is going to give us H2O plus NAD+. And then whenever we reverse that reaction, we also reverse the sign, so it's no longer going to be negative 0.32, it's going to be positive 0.32, and because we've coupled these reactions together, we're just going to add them together to get our value of 1.14 volts. So that's our example of our half reactions. So another example of this can be if we're looking at NAD and ubiquinone. So again, we're going to look at this reaction here. So we have a negative 0.32, and then we look at our ubiquinone, we have a positive 0.10. So where are the electrons going to flow? They're going to flow from the NADH to the ubiquinone. So we know that that's going to happen. So what I want you to do is I want you to write out the two half reactions, then I want you to write out the final full reaction and determine the E0 prime from that. The last component of this particular presentation that I want to go over with you is how can we determine delta G0 prime. So what I'm asking here is, are these reactions spontaneous? Because the reduction potential is not the same thing as our Gibbs free energy, but there is an equation that allows us to determine that. So that is this equation. So our delta G0 prime is equal to negative NF times the change in delta E0 prime. So again, from the example given to you in class, right? So if we have our delta G0 prime, if we're looking at the example written that's already on your handout, we would have negative 2 electrons, so 2 for the N. Our Faraday's constant, that's always going to be 96,485 joules per volt times mole. And we're going to multiply that times the change in E0 prime. And for ours, it was positive 1.14. And then you're going to be able to calculate out the delta G0 prime, and you're going to determine for that particular one that it's going to be negative, and so if it's negative, that means that it's spontaneous. So what I want to note to you is that the more positive the E0 prime is, the more negative the delta G is going to be, and so it's going to be spontaneous. And if the delta E0 prime is negative, delta G is going to be positive, and so it's going to be non-spontaneous or endergonic. So that was my brief overview of redox reactions, and so we're going to go over a couple more examples in class.